we are picking up here with colligative properties. What colligative properties are and what makes them so special is these are properties of a solution, and these properties are dependent on the amount of solute that you have in a solution, and they are completely independent of the type of solute. It does not matter what the solute is. All that matters is how much of it there is. So you could have one solute molecule, and you have maybe a concentration of 0.1 molar, and then you have a different solution that has a completely different solute. But if it also has a concentration of 0.1 molar, these colligative properties will be identical in the two different solutions. They are only dependent on the amount of stuff. They are not dependent on the identity of that solute. So again, these are called colligative properties. So let's talk about the first one here. So the first colligative property we're going to see is what's called vapor pressure lowering. This is when you have a non-volatile solute. The main reason here that it needs to be non-volatile is because you don't want the solute escaping, because then the solute's gone, and so it can't do its job in the solution anymore. So if you have a non-volatile solute, so a solute that's going to stay in solution, if it's in the solution there, what will end up happening is that because it's dissolved in the solution, that just inherently means that it has some strong intermolecular forces with the solvent molecules. And so because of those strong intermolecular forces with those solvent molecules, it makes it less likely for the solvent molecules to escape from the solution. Essentially, there's another thing there kind of holding on to the solvent molecules, making it more difficult for them to escape. And so as a result, the vapor pressure, the amount of the solute that is going up and into the gas phase, decreases when you make a solution relative to just the pure solvent. One of the kind of cool side effects of this is what we call thirsty solutions, where if you put two different beakers into an airtight container, like you can see here, and if one of them is a solution and the other one is not, and the more concentrated the solution is, the better this works. As the solvent molecules, and the solvent has to be the same for both, so these would have to be both water, for example. As long as the two solvents are the same, this will work. As the solvent molecules start to evaporate, they start to go into the gas phase, the solution, just the pure solvent over here, will have more going out into solution, or into the gas phase, than the concentrated solution does. And as the container fills up with the gas, you'll have a few molecules being recaptured into the pure solvent, but even more get captured into that concentrated solution that you had over here. And so if you sit and watch it for long enough, and this isn't something that takes, doesn't happen over the course of seconds. It takes hours for this to happen. But if you, for example, just set it there and then come back the next day, it will appear as if using some kind of invisible straw, the concentrated solution sucked the solvent out of this other beaker, because you will actually increase the volume of the solution as you decrease the volume of the pure solvent. So it's pretty cool, actually. It's a very strange thing to see, but it does happen. The equation that we use to quantify exactly how much the vapor pressure is lowered is called Raoults law, and I think I'm pronouncing that correctly. If anyone knows a better pronunciation, feel free to let me know. But Raoults law describes vapor pressuring, and it tells us that the pressure of the solution, and by the way, this is not a negative sign, it's just a bullet point. So the the pressure of the solution, the vapor pressure of the mixture of solvent and solute, is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So notice here we're not using the mole fraction of the solute, the thing that is dissolved. It is the mole fraction of the solvent, the thing you have more of. That is the mole fraction that you're going to use. And so using this, we can find the lower vapor pressure of these solutions. Now, it is possible that you could have multiple things dissolved in the solution, and especially if they're both volatile components where you have things that are going up into the gas phase, it can get really complicated. We are not going to get into that at all. We are just going to stick with having one non-volatile solute in the solution. So let's look at a quick example here. This asks us to compute the vapor pressure of an ideal solution containing 92.1 grams of glycerin and 184.4 grams of ethanol at 40 degrees C. The vapor pressure of pure ethanol is 0.178 atmospheres at 40 degrees C. Glycerin is essentially non-volatile at this temperature. So why don't you go ahead and try to solve this problem. So go ahead and pause the video and try to work out the vapor pressure of this solution. Alright, I hope you gave that a shot. As it says here, we're trying to find the vapor pressure of the solution. And so we're going to use Raoults' law to do this. And so we need these two things, essentially. We need the mole fraction of the solvent, and we need the vapor pressure of the pure solvent. This already given to us. We've got it. It's right there. Because the ethanol is the solvent, we have more of it than we have glycerin. So we have the vapor pressure of our pure solvent. So we just need the mole fraction. So in this case, we have some gram to mole conversions to do, because we're given masses for both of those, but we need the number of moles. So just for the sake of time, I'm not going to write those out there, but I'm going to go ahead and work through them on my calculator. Let's see, so glycerin is 3 times 12.01 plus 8 times 1.008 plus 3 times 16. So glycerin is 92.1 essentially grams per mole, and the ethanol is 46.07, we'll say. Grams per mole. Sorry, ran out of room there. Okay, so if we do those conversions from grams to mole real quick, what you might notice is that this one, hey, look at that, we have 1 mole. Who would have thought? It's almost like they did that intentionally. So we have 1 mole of the solute. And then let's see, we have 184, and if I remember correctly, this is going to work out to be an even number as well, but I'll double check. Yep, essentially 4. 4.002604, we'll just go with 4.00. Now this is where, if you made a mistake, you probably made a mistake. This is the most common error here, is you get the number of moles for both of these things, and then you say, okay, moles of solute divided by moles of solvent, or Moles of solute divided by the moles of everything. Remember, Raoults' law is not the mole fraction of the solute. It is the mole fraction of the solvent, the thing you have more of. So our mole fraction is 4 moles divided by 5. The number of moles of solvent divided by the number of moles of everything, which is just 4 plus 1. And so this is going to be, oh, I should probably be able to do that in my head, but it's late. So 0.8 is our mole fraction. And so to get the vapor pressure of our solution, that would be 0.8 times 0.178, which is 0.142. Let's see, I really should only have 3 sig figs there, so we'll just leave it at the 2 atmospheres. Which is a pretty significant decrease. Like, it's not 50% or anything like that, but that is not a tiny decrease in the vapor pressure for our solution. Alright, we'll leave it there for now, just because I don't want to make this another 30-minute video like the last one. So we'll look at the other colligative properties in the next video. So I'll see you there.